Good morning, friends and dear students. It gives me immense pleasure to be here for my course, Engineering Thermodynamics. Today, my topic is tutorial on thermodynamic concepts of pure substances. I am Dr. Dwivedi, professor from Department of Aeronautical Engineering, Institute of Aeronautical Engineering, Hyderabad, India. I have started this course, and this is my third lecture. Before that, we have already completed the basic concept and what is the pure substances and how this thing can be converted from one phase to another phase. We have seen that there are the three phases: solid, liquid, and the gaseous, and how this thing can happen. We have also seen that how the critical point and the triple point of the substance vary with respect to the pressure, temperature, and specific volume variation. This we have already covered. In today's class, I am going to take two problems related to the pure substances. That is the problem 1 related to the pure substance. Then the next issue is regions of the substances, the ideal gas equation of state, compressibility factor, and next is the problem number 2. So these topics I am going to take in this next 35 to 40 minutes. Before that, I will try to revisit my previous lectures and the topics which I am telling as the revision of my last lecture. In that, I have covered the pure substances. The pure substances are the substance in which they behave like a homogeneous if you mix two or more substances. Then I have also covered the phase change process. I have shown in PV and TS diagram. Then properties of the substances. I have shown the steam table. Then property relationship and the quality of mixture. So you may be remembering that if I draw the PV diagram, so it is like this, and this is called the critical point. Critical point. And if you see here, from this will go from here to here, and from this is the saturated liquid line, and this is the saturated and this is the saturated liquid line. So if any process, it goes like this, and as and when it is coming to the saturated liquid line, from here phase will change, and inside this zone this is the mixture of liquid and the vapor. Here if you see, it is a total vapor. Here the quality is equal to 1, and here x, the quality is equal to 0. So if quality is equal to 0, it is a liquid, and if quality is equal to 1, this all liquid has converted to the steam. If you see here, if I take a container here and there is a water, this is the water, and if we give heat from here, we just burn something and heat is given Q, heat is Q, and if you make it, so as and when this vapor will start forming, and if you just close it like this and you give the temperature, and this, after reaching in this position, all it will start here vapors, and as you reached up to this point, your all this water has become the vapor. So it is from here, it is a dry vapor, it is no water mixture here. As you go up, it is a dry saturated vapor. Vapor is formed. So this is the process in which we have discussed in TV, and the same way you can make in TV diagram. And there are number of properties, which properties like pressure, temperature, your this saturated specific volume, then vapor volume, specific volume, internal energy, enthalpy. These all parameters we can see in a steam table, which we have already seen in my last class. And there is some property relationship we have seen how these things are varying, and we have derived the equation for the quality of the vapors and qualities of the mixture we have already seen in my last class. Now I will go for the first problem of my this course. A closed rigid container of volume 0.5 meter cube is placed on a hot plate. Initially, the container holds a two-phase mixture of saturated liquid water and saturated water vapor at P1 is equal to 1 bar with quality of 0.5. After heating, the pressure in the container is P2 is equal to 1.5 bar. So what we have to find out? We have to indicate the initial and the final state on a TV diagram and determine A, the temperature in degree centigrade at each state. Number B, the mass of vapor present at each state in kg. C, if heating continues, determine the pressure in bar when the container holds only saturated vapor. So these are the conditions which are given here, that a closed rigid container of volume 0.5 meter cube. So a container which is closed like this, it has got 0.5 meter cube of volume, and this is placed in a hot plate. This is the hot plate here. It is heated by some heat is given. Initially, the container holds a two-phase mixture. So initially, here we have the two-phase mixtures are there. So here it is the water here. This is the water, and here these are the vapors. So water and vapor mixtures are there, and this temperature, this pressure is P1 is equal to given here 1 bar, and quality X of initial is 0.5. So means X initial condition is 0.5. If we give the heat, the pressure in the container P2 becomes 1.5 bar. Indicate the initial and the final state on a TV diagram. So we have to show first that how the TV diagram, temperature and the specific volume of this system, and also to determine the temperature in degree centigrade at each state. So this state 1 and state 2 temperature we have to find out. That is the first case. Then the second case, the mass of the vapor present in each state. So how much At the P1, how much is the mass of the vapor, and at the second stage, how much vapor is there. If heating continues, third point, determine the pressure in bar when the container holds only saturated vapor. So we have to see that how much container it is containing the saturated vapor. So that is our problem statement, and now we have to solve this problem. So to solve this problem, we should have some assumptions for solution of the problem. Assumptions are: water in the container is a closed system. 2. States 1, 2 and 3 are in equilibrium state. The volume of the container remain constant. So means whatever volume is given, it is constant, and it is a closed system. So what is the closed system? What is the meaning of the closed system? Means if this is the system, mass is not taking, mass is constant. Mass will not cross the boundary. So mass will not cross the boundary. That is called the closed system. So mass will remain inside the system only. That is the first thing. It is a closed system. States 1, 2 and 3. So state 1, 2 and 3 all are in equilibrium. Equilibrium means it is mechanical equilibrium, thermal equilibrium and chemical equilibrium. All types of equilibrium, and the volume of the container remain constant. So it will contain the same amount of volume. So that is the first assumptions which we have taken. And for solving this type of problem, we have to see that we are doing the same thing. Here we need two independent properties are required as per the Gibbs equation, required to fix state 1 and 2. At the initial state, the pressure and the quality are known. So for the P1, for the point 1, the pressure is known and the X value of the first is given. Thus, state 1 is known. As mentioned in the problem, the specific volume at state 1 is found using the given quantity. So we can find out the specific volume at state 1, that is V1 is equal to Vf1 plus X1 Vg1 minus Vf1. G is for gas, F is for liquid. So if you see here, this is the F and this is the G. So if this is the 1 here, 1 point, so here this is the Vf1, here this is the Vf1 and here is the Vg1. This can be found out from the steam table. Every steam table will give this situation. So from this we can find out the specific volume at the given condition. So from a table at P is equal to, from steam table at P is equal to 1 bar, it is also called the 100 kilopascal. 1 bar is equal to 100 kilopascal. So in this we have got that all this parameter. We have got Vf1 0.001043. Then we got Vg1, that is this point. We got, this will be always more than this, 1.694, and this value we have to, and this x1 is given. So x1 is given is 0.5. This from the steam table, this from steam table, this from steam table. If you put this value, we will get the specific volume. This is the specific volume at state 1. So this quantity we have got, and if you calculate, we will get 0.8475 meter cube per kg. Now we have to see that at state 2, the pressure at state 2, the pressure is known, volume and mass remain constant during the heating process within the container. So volume is constant. So V2 is equal to V1. For P2 is equal to given 0.15 megapascal. So from this table, from steam table, we can find out that Vf2 is equal to 0.001053 and Vg2 is equal to 1.1593 meter cube per kg. This we can get from table that is called steam table here. And in this pressure we have to find out that what is the Vf2 and the Vg2. And the same way as before, we can see here that this Vf2 is less than V2 and the Vg2. So whatever we have Vf2 and the Vg2, and so this V2 which we have got 0.8475, this is in between Vf2 and Vg2. So state 2 must be in the two-phase region as well. So I will just show here that it's PV diagram. So it is like this. So this is 1 and this is somewhere, this is the 2. Here is the 1 and this is the 2. Okay. So if here this is the Vg2. So here if you see here that we have find out Vf2 and the Vg2, and this number, because V2 is equal to V1 and this V1 is in between Vf2 and the Vg2. So it is not in the vapor line, it is before that. So this we can ensure by this way that the state 2 is not in the gaseous form. It is not fully in gaseous form. It is before that. So it is in the liquid and the vapor region. The temperature corresponds to the saturation temperature of the given. So here we can see that we can find out from TS diagram, T and V diagram, and how it is shown here. So from the steam table, in the given condition, we can find out that this T1, this is the 2 and this is the 3. All are in the constant volume. Here is P1 is equal to 1 bar, P2 is equal to 1.5 bar here, and this is not here. So we have to extend this thing at constant volume. So here we can get that this T1 from steam table, we will get that 99.63 and T2 is equal to 1.4 degrees centigrade. This is the T2. So these two value we have got. Now to find out the mass of the vapor present, we first find the total mass M. So what is the total mass? We know that specific volume is equal to volume per unit mass. So mass is equal to specific total volume divided by specific volume. So total volume is given in the question is 0.5 meter cube, and we have got this V specific, we have got 0.8475 meter cube, so it is kg. So we have got the mass 0.59 kg is present in the system. Now we can see that mg1, mass of the gas, is equal to x1 into m. So it is x1, it is given as a 0.5 into 0.59. So 0.25295 kg. This we have got from this as the how much gas is there or the vapors are there. The mass of the vapor at T2 is found similarly using the quantity x2 from the table of steam table for P2 of 1.5 bar. So we can get that X2 here is equal to V minus Vf2 divided by Vg2 minus Vf2. It is equation to find out the position of or the quality of gas at the point 2. So V minus Vf2, Vg2 minus Vf2. So we know all these parameters, this one, this one, this one, this one. We have to find out from the steam table, and we can get X2, the quality. This is called quality of steam at state 2. So this X2, we have got that 0.8475 minus Vf2 0.001053 divided by Vg2. Vg2 is equal to 1.159. This is from steam table, all these parameters, minus 0.001053. So you will get the 0.731. X2 is equal to 0.731 and X1 we have already given is 0.5. So if you see here, this is the 0.5 and next is this is 0.731 X2, X1 and this is the X2. So like this. So from here we can see that what is the mass of the gas? Mg2 is equal to 0.x2 minus mass 0.59. So 0.431 kg. So in this way we can find out the mass at the point 2. So if heating continues, then state 3 would be on the saturated vapor line as shown in the TV diagram above. Thus, the pressure would be the corresponding saturation pressure interpolated in table A5 at Vg is equal to 0.8475 meter cube per kg and we get the pressure 2.11 bar. So this you can see here, the state 1 and 2 we have find out. Now how we have to extend it, and as and when it is touching here, and in this we will get that what is the pressure, and this is possible as shown in TV. If the pressure would be the corresponding saturation pressure, so interpolating by the steam table, this is the steam table here, at Vg is equal to 0.8475 meter cube per kg, and so we get P3 is equal to 2.11 bar. So this we can say that this is the pressure of the gas at state 3. So one first problem is done. Further some clarification and some other things are needed. So, and after that I will again go for my next problem. So superheated vapor. So superheated region is a single phase region, that is the vapor only. Temperature and pressure are no longer dependent. So if you see in this diagram, this is the T and V diagram. So here this is called the compressed region. This is the saturated liquid vapor region. Here it is a combination of liquid and the vapor, and if you go here, they are as a superheated region. So superheated vapor means there is no water available. It is fully gas condition, and this line, this is the critical point, and from here to here it is called the saturated vapor line, and from here to here it is called the saturated liquid line, and in between from here to here this is the mixture of saturated liquid vapor. Here pressure and the temperature will remain constant. As and when you go away, the pressure and temperature will be independent. But here pressure, but here both are dependent, which I have discussed in my previous class. If you see in this region from here to here, if you draw this P and T, it is like this. Means for a particular T, there will be a constant P. For next T, constant P. This will be applicable for this zone only. Here, both are not independent. P and T are both related in saturated liquid vapor region. But if you go here, we need the pressure and the temperature, both are separate. Both are independent. But here, both are dependent. If you increase the T, P will also increase in the same ratio. There will not be, just like I have shown here. But this will not be valid in this zone. It is called the superheated zone. The superheated zone, in that there is no vapor. All the liquid is converted to the vapor and it is fully dry saturated. There is no vapor at all. So, if you see here that the superheated region is a single phase, there is no vapor or there is no liquid, only the vapor is there. Temperature and pressure are no longer dependent. In this region, P and T are dependent. So, the table A6 for superheated vapor property, if T is greater than the T critical or P is less than P critical, then it is called the superheated vapor zone. Inside the dome, so if you see here, this is called the dome, this black line from here to here, this is called the dome. Inside the dome, the temperature remains constant and is also as saturation temperature. This is called the saturation temperature. Above the critical point, there is not much difference in saturation liquid and the saturation states. So if you go here above this, there is no saturation state. Above this critical point, there is not much difference in saturated liquid and the saturation vapor state. At any point inside the dome, if you see inside this anywhere in this dome, if you see in this dome, at any point inside the dome, the quality of the mixture is defined as the ratio of the mass of vapor to the total mass of the mixture. So this is quality of X is equal to mass of the vapor divided by total mass M. So this is called the X. So this is the situation. Compressed or subcooled liquid. If you see here, this zone is a compressed or the subcooled, and here is the superheated region. So what is the compressed region or the subcooled? This is also called the subcooled. So this I am going to discuss in next slide. So compressed or subcooled liquid. The properties of a liquid are relatively independent of pressure, that is incompressible. A general approximation is to treat compressed liquid as saturated liquid at the given saturation temperature. So here Vf, F indicate this point is F and this point as a G. So we can consider here that the saturation pressure and the saturation temperature, we can consider that it is a Vf. So of any property, let it be pressure or temperature or anything, a general approximation is to treat compressed liquid as saturated liquid at the given saturation temperature, or Y is equal to Yf at given temperature. The properties most affected by pressure is enthalpy. For enthalpy, use the following approximation. So enthalpy is given by H, and this H is approximated as HF at T plus Vf P minus P saturation. So this is the enthalpy which is affecting. So if you take anywhere, so first you have to take, if you mark here H. So if it is like this anywhere, so it is H. So this is the H FT plus wherever is the location, the Vf into P minus P saturation. So here is the saturation pressure. So like this we have to consider for this enthalpy. Now I will discuss about the ideal gas equation of the state, because for the thermodynamics we are most of the time we take the gases as the ideal gas, and ideal gas should have some special properties, and that is we have to relate. So any equation that relates the pressure, temperature and specific volume of a substance is called an equation of state. So any mathematical equation that relates the pressure P, temperature T and specific volume. So specific volume is the volume per unit mass. Then it becomes the property. That is the independent or intrinsic property. If you take the total volume, it is not intrinsic. So if you want to make as a property, you should always take specific volume, not the total volume. And this specific volume is mentioned as small v. So this small v is equal to total volume V divided by per unit mass, and this is the meter cube per kg, and this is the inverse of the density, and this is equal to 1 by rho, and the rho is a density. So we have seen in our previous classes, our intermediate and high school, we have seen the density. We have studied about the density of water, density of oil, density of petrol and all. But we have not much focused on the specific volume. Specific volume is nothing. It is a inverse of the density. Density is kg per meter cube and specific volume is meter cube per kg, and that is the per unit mass, the volume per unit mass. So if you want to make the volume as a parameter for your property, then it should be divided by mass. Then only we can take it as a specific this property. So if you want to relate the different properties of pressure, temperature and the specific volume, that equation is called the equation of state. So next is the simplest and the best known equation of state for substances in the gas phase is the ideal gas equation. So the best equation which relates this pressure, temperature and the specific volume is called the ideal gas equation. Gas and vapor are often used as a synonymous words. So if it is vapor or the gas, both are the same. If it is water and water is heated, we normally say it is vapor. But for air and all, we don't say the vapor, but both are the same. We say the gas, nitrogen, carbon dioxide, oxygen, we say the gas. But once we make from the water, we evaporate, then it becomes the vapor, but both are same. Both are, we have to consider synonyms, and both can be used as a interchange words. The vapor phase of a substance is called a gas. So once we boil the water and the total liquid is converted to the vapor, then we can say that this is a gas. So a vapor phase of a substance is called a gas when it is above the critical temperature. So if we are making it above the critical temperature, the vapor phase is called the gas. Vapor usually implies a gas that is not far from a state of condensation. So vapor usually implies a gas that is not far from a state of condensation. It is experimentally observed that at a low pressure, the volume of a gas is proportional to its temperature. So once we have done some experiment and it is proved that at a low pressure, if the pressure is low, the volume of a gas is proportional to its temperature. So V is directly proportional to the T at low pressure. This we have to understand. And this is called PV is equal to RT. This gas equation is called P is a pressure, V is a specific volume, and this is the R into T is a temperature, and this is a gas constant, universal gas constant. Where R is a gas constant, the above equation is called the ideal gas equation of state or ideal gas relations. Since R is a constant, so if this R is constant, it is a constant value, so we can write that R is equal to P1 V1 by T1 and is equal to P2 V2 by T2. So this is, we can make in this way as R is constant, where 1 and 2 denotes two states of an ideal gas. The constant R is different for each gas. So this R is for air, it is different; for oxygen it is different; for hydrogen it is different; for CO2 it is different. For different gases, this value of R will be different. Now I will further give some values. So this Ru is a universal gas constant and this is same for all. So Ru is equal to 8.314 kilojoule per kilomole per Kelvin is the universal gas constant. So R is equal to gas constant, R is equal to Ru by M. This we have to very much careful that it is R is not Ru. But Ru will always same. It will be 8.314. We have to remember it, and it divided by the molecular mass of this any gas. The molar mass or molecular mass, that is M, is equal to kg per kilomole, is defined as the mass of 1 mole of a substance. The mass of a system is equal to the product of its molecular mass M and the mole number N. So this molecular mass is defined as the mass of 1 mole of a substance. Means for 1 mole, what is the mass of that thing? The mass of a system is equal to the product of its molecular mass and the number of mole. So number of mole, how many are there, multiplied by the molecular mass. This is called the mass of a system. So this mass M, small m, is equal to mass of a system is equal to M is equal to molecular mass into number of moles. An ideal gas is an imaginary substance that obeys the relation PV is equal to RT. So for any ideal gas, which is normally not found in the real scenario, but we take some assumptions and we do some calculation keeping that it is an ideal gas. So in that it will follow that PV is equal to RT. It is experimentally observed that the ideal gas closely approximate the PVT behavior of real gas at low densities. So it is experimentally observed that the ideal gas closely approximate the PVT behavior of real gases at low densities. In the range of practical interest, many familiar gases such as air, nitrogen, oxygen, hydrogen, helium, argon, neon and carbon dioxide can be treated as ideal gas with negligible error. These are the monoatomic gases, and this we can see that if these gases are there, we can use this PV is equal to RT because their errors are very less. Water vapor refrigerant vapor in refrigerator should not be treated as ideal gas. So we have to understand that water vapor, refrigerant vapor, this we cannot take as ideal gas because they are in the two-phase system. Water vapor at pressure below 10 kilopascal and can be treated as the ideal gas regardless of the temperature. If the pressure is very low, means less than 0.1 atmospheric pressure, we can say that it is a ideal gas. So we have done about ideal gas and its functions. Now we have to see that what is the compressibility factor Z. So the assumption of ideal gas relation implies that the gas particle take up negligible volume. So for the ideal gas, what we have assumed that the gas particle takes up a negligible volume. The intermolecular potential energy between particles is very small. Particles act independently on one another. These are the few assumptions we have to take for ideal gas. Real gases deviates from ideal gas behavior, but the real gases are not like the ideal gas. This deviation is given temperature and pressure can be accurately accounted for by introduction of a correction factor called the compressibility factor. Okay, so just I want to again emphasize here that the compressibility factor is used to apply the gas equation for a real gases. For the ideal gas, in fact, in the real scenario, ideal gases are not available. But to calculate this pressure, specific volume and the temperature of different applicable or the used gases, we have to apply a compressibility factor to make the result accurate. And that compressibility factor is called the Z, which is accounting for a real value, accurate value of different properties. This compressibility factor Z is equal to PV by RT, or PV is equal to ZRT. This Z will have some values. So here Z is equal to V actual by V ideal. The volume of any gas is actual, how much is there, and for the V ideal, how much is there. Obviously, J is equal to 1 for a ideal gas. So if it is the Z is equal to 1, it is a real gas. But in the real field, you won't get Z is equal to 1. Gases behaves very much the same at temperature and pressures, normalized with respect to their critical temperatures and the pressure. So if you normalize the pressure and the temperature with respect to their critical temperature and the pressure, that is P critical and the T critical, if you divide, then you will get here what is the meaning of PR is equal to P by P critical and TR is equal to T by T critical. Here PR and the TR are called the reduced pressure and the temperature respectively. By curve fitting all the data, the general compressibility chart is obtained, which can be used for all gases. So this PR and the TR, which are the reduced pressure and the temperature, by the curve fitting of the all data, and this we can see here that reduced pressure in the x-axis, and the here is the Z is equal to PV by RT. And so for the different gases, we have here methane, isopentane, ethylene, N-heptane, ethane, propane, butane, water, carbon dioxide, nitrogen, all average curve based on data on hydrocarbons. So here this you can see that at different PR, here we have the TR for different cases. TR is equal to 2, TR is equal to 1.5, 1.3, 1.2, 1.1 and 1. Okay, so like this we can find out the value of Z at a given temperature and the given pressure. So in this way we can find out the compressibility effect, and these numbers which we have to use it may be, you can see here it is 1 here, and most of the time you will get less than 1. Value of Z will be less than 1. So figure here Z factor, general compressibility chart, reference 2. So from the Z chart one can conclude that at very low pressure, when PR is less than 2, ideal gas behavior can be assumed. So if the PR is less than 2, we can assume that this is the ideal gas. The deviation is highest in the vicinity of the critical point. But at the critical point, these things are very much high. So if you see here, so less than 2 means if Z is less than 1, we can conclude that this is the ideal gas. So now the next problem, problem number 2 here. This we can see that how much it is going, that determine the specific volume of R134A at 1 megapascal and 50 degree centigrade using A, ideal gas equation, B, the generalized compressibility chart. Compare the values obtained with actual value of 0.02171 meter cube per kg. So here we can see that from the, this is the R134 refrigerant. There is a table for this refrigerant. From there we got that R is equal to 0.0815 kilopascal meter cube per kg Kelvin, and critical pressure is 4.065 megapascal, and critical temperature is 374.3 Kelvin. These are the items we can get from the steam table. In this problem we have given that T is equal to 50 degree centigrade or 273 plus 50, we will get 323 Kelvin. P is given 1 megapascal, that is the 1000 kilopascal. We have to convert all mega or anything into kilopascals, because your steam table is given in kilojoule and kilopascal. Every parameter should be in kilopascal, not only pascal or not in megapascal. That we have to keep in mind. So for an ideal gas equation state, we can PV is equal to RT. So from here R is given here. This you can see that R is this much. R T is, we got that 323 divided by 1000 kilopascal. We will get the specific volume as 0.02632 meter cube per kg. This we have got the specific value. Comparing with the tabulated value using ideal gas equation, one would get an error of how much we are going to get the error. This you can see here. This we have got here. But from here we got this much 0.02632. 0.02632 minus 0.27171. 2171 divided by 0.2171. So here we will get 0.212 or 21.2% error is there. So for this equation, and what we got from actual measurement, there is a 21.2% of error which we can experience. So to determine the correction factor, that is the Z, so here PR is equal to P by PR. So here P is equal to 1 megapascal and PCR, that is the critical pressure, is given 4.067. So you will get the PR is equal to 0.246 and TR is equal to 323 by 374.3. So you will get the 0.863. From the figure, we can see that Z is equal to 0.84 by considering PR and TR. Thus, V is equal to ZV ideal. So 0.84 into V ideal is this much. So we will get the actual specific volume 0.02211 meter cube per kg. The error is less than 2%. In the previous it was 21.2, but when we apply this Z, error is tremendously reduced. That is the topic where we can work and we can do some research. Therefore, in the absence of exact tabulated data, the generalized compressibility chart can be used with confidence. So if you use this compressibility chart which I have shown in the previous one, this is very useful for the calculation of different data. These are the one more problem, and these are the tables which we can use for our purpose. For different steam tables we can find out. So these are the references from P.K. Nag, that is Engineering Thermodynamics, Tata McGraw-Hill's, Yunus Senjel, that is the Thermodynamics and Engineering Approach, and this is the video which I have taken from NPTEL from Professor Mishra. I have taken some content from there. Any questions you are welcome to ask. My email ID is dwivedi@email.com. Please do like this channel and subscribe. Thank you very much for listening to me. I will be also taking next class related to the 0th law of thermodynamics, and then I will go for the first law of thermodynamics. I will also solve some more problem which will be very useful for you all. Thank you very much.
Like, share and subscribe. Hit the bell icon for more updates.